So I saw a video the other day from a YouTube creator, Black Pin Red Pin. He does math videos. It's good stuff. You should check it out. At one point he wrote down the complex values of the cube root of 8 from memory. And that got me thinking about how you could calculate that value. And apparently he was thinking the same thing. So later I noticed that he had a video about how to calculate the complex roots of the cube root of 8. In that video, he calculates the complex cube roots of 8 using factoring. To watch that video, you can click on the link here in the upper right, or I've left a link to it in the description for this video. Check it out. However, my idea was that you could calculate a cube root a little more graphically, and in fact, it's so easy that, assuming you can put a couple of pieces together that you probably already know, that you can do that calculation in your head for just about any complex cube root, assuming that you know the principal cube root for that number. So let's take a look at how that's done. So we start with the idea that we have the cube root of 8, and of course this equation means the principal cube root of 8, in other words the real root, which of course is 2. So if we were to graph all of the complex numbers that have a radius of 2 on the complex plane, we'd get this circle. What we're going to do is we're going to divide the circle by the order of the root that we're looking for. So in other words, 360 degrees divided by 3 equals 120. So if I were to plot those points, again staying within the radius of 2, because that's our principal root, we would have a point at 120 degrees, and we would have a point at 240 degrees. So these 2 points, along with the principal root, represent all of the solutions to the cube root of 8. Now the trick is, how do we calculate those values? And it turns out to be pretty simple. You could use the Pythagorean theorem, or you could use a little basic trigonometry. So let's calculate the first complex root. And what we'll do here is we'll put a triangle on that line. Now, of course, we could think of this as 120 degrees, but we could just as easily think of it as 60 degrees inside of the second quadrant. So if we get the sine of 60, we can see that that's 0.866. But if you remember your basic trigonometry, you know that that is more accurately represented as radical 3 over 2. And the cosine of 60 is 1/2. Again, remembering we're in the second quadrant, so that's negative 1/2. And the Pythagorean theorem tells us that those are actually the legs of the triangle that we just created. Now we apply the fact that this triangle has an hypotenuse of 2, so we multiply our trigonometric values by that hypotenuse value of 2. So our triangle has an hypotenuse value of 2, it has an x value of -1, and an imaginary value of radical 3. And so those are the coordinates of our point, which again, remember, is a point on the circle that represents a complex value that has a radius of 2. So our point then becomes -1, radical 3i. So that's the first complex root of the cube root of 8. And then we flip that triangle down. In other words, we go into 240 degrees, and we use similar logic, but this time both our x and imaginary values are negative. So the point that represents the complex root of the cube root of 8 becomes -1, radical 3i. So now we have our 3 points, where each point represents a cube root of 8, and we create those complex cube root values simply by taking the x component and combining it together with the imaginary component. We see those points and their corresponding complex values here. The principal cube root is 2. The first complex root is -1, radical 3i, and the second complex root is -1, radical 3i. Now the real magic here is, let's consider another cube root. Imagine instead of a radius of 2, we have another circle of radius 1. So the points of this circle represent all the complex values of a number with a radius of 1. So what we have here is that the principal cube root of 1 is 1. And by the same trigonometric logic that we went through before, the first complex cube root of 1 is -1/2, radical 3 over 2i. And the second complex root is negative 1/2 negative radical 3 over 2I. In other words, the form of the point is exactly the same as it was for the larger circle of radius 2. These two complex cube roots only differ from those complex cube roots by the radius of the circle, which is to say the value of the principal cube root. And just as a final example, we'll use the cube root of 125 so we can see the same thing. The principal cube root is 5. The first complex cube root is negative 5/2, 5 radical 3 over 2I. And the second one is negative 5/2, negative 5 radical 3 over 2I. And again, we can see that these values differ from the other cube roots that we calculated only based on the radius of the circle, which again is the value of the principal cube root. And then to generalize that for our three examples, we see that the complex cube roots can easily be generated simply by multiplying by the value of the principal cube root. So on the left here, we see the generalized formula. Now I suppose if you wanted to take this one step farther, we could further generalize the expression using sine and cosine. So use whichever is easier to remember. So in this way, you can easily calculate the complex cube roots of any number pretty much in your head. Thanks for watching.